In this lesson, we will learn the limit laws, which will make it a lot easier for us to determine the limit of a function as x approaches a. So for that, let's look at the graphical representation of a few functions which I have right here. So here you can see I have taken three functions. The expression for the first is x, and the expression for the second is x square, and the expression for the third is x plus x square, which is the sum of these two functions x and x square. Now before we proceed further, let's quickly determine the limit of all these three functions. For example, say as x approaches 2. Now, as we have been learning the meaning of the limit of a function as x approaches a graphically for the past two lessons, so I will go over it relatively quick. So for this function, as x approaches 2, the values of this function approach the number 2. So I can write that this function approaches 2 as x approaches 2, and which means that the limit of this function x as x approaches 2 is equal to 2. Similarly, for the function x square, we can see that as x approaches 2, the values of this function approach the number 4. So, which means that x square approaches 4 as x approaches 2, and which means that the limit of x square as x approaches 2 is equal to 4. And there must be no problem in writing this statement as this statement. We have been learning this for the past two lessons. Now let's see the limit of the function x plus x square as x approaches 2. So as x approaches 2, the values of this function x plus x square approach the number 6. So we can write this as x plus x square approaches 6 as x approaches 2. So what do we observe here? See, as x approaches 2 and x square approaches 4, their sum, which is x plus x square, which is right here, approaches the sum of 2 and 4, which is 6. So I can write this as 2 plus 4. Now, what is the meaning of this statement? This statement means that this 2 plus 4, that is 6, is the limit of this function x plus x square as x approaches 2. So, we write it symbolically as limit of x plus x square as x approaches 2 is equal to 2 plus 4. Now I'm writing limit of x as x approaches 2 for 2 and limit of x square as x approaches 2 for 4 to get limit of x as x approaches 2 plus limit of x square as x approaches 2. I will quickly write it as limit of x plus x square as x approaches 2 is equal to limit of x as x approaches 2 plus limit of x square as x approaches 2. Now this is what I wanted to show you. It tells us that the limit of the sum of these two functions is equal to the sum of the limits of the individual functions. And this is called the limit law of addition. Now let's quickly write down this limit law for the functions in general. Suppose I have a function fx whose limit as x approaches a exists and is equal to the number p. And similarly, let's say I have a function gx and whose limit as x approaches a is equal to the number q. Now we have been learning this for the past two lessons, and we know that fx approaches p and gx approaches q as x approaches a. Now just a few seconds ago we had seen in the graphical representation that for the function x approaches 2 and for the function x square approaches 4 as x approaches 2. And then we had seen that the sum of x and x square, that is x plus x square, approaches 2 plus 4, that is 6, as x approaches 2. So similarly, as fx approaches p and gx approaches q as x approaches a, it is logical to say that the sum of f and g approaches the sum of p and q. So we can write fx plus gx approaches p plus q as x approaches a. It means that this number p plus q is the limit of this function f plus g as x approaches a. See, when we say fx approaches p as x approaches a, it means that this p is the limit of f as x approaches a. In a similar manner here as well, we see that f plus g approaches p plus q as x approaches a. It means that this p plus q is the limit of f plus g as x approaches a. So we can write this result as the limit of fx plus gx as x approaches a is equal to the number p plus q. Now, let's write it quickly as limit of f plus g as x approaches a is equal to, now what are these p and q? So, this p is the limit of f as x approaches a and q is the limit of g as x approaches a. So I'm going to write down this for p and this for q. So we get this as limit of f as x approaches a plus limit of g as x approaches a. And now we have arrived at an important result, and this is called the limit law of addition, and which says that the limit of a sum is equal to the sum of the limits. Now this law together with more limit laws helps us determine the limit of a function as x approaches a without making the table of values and guessing the limit of a function as x approaches a, or even without using the graphical representation of a function. And before we learn how to apply this limit law, let's first discuss a few more limit laws. So the next I'm taking is the limit of a constant as x approaches a is the constant itself. Now the proof of this limit law is pretty intuitive. Let's look at it graphically. So suppose I have here the coordinate axis where this is say 0, this is our x-axis, this is our y-axis, and let's say a line parallel to this x-axis is y is equal to c. That means all along this line, whatever be the value of x, y remains the constant and which is c. Now let's take a particular number, say a on the x-axis, and it's clear that to this number a on the x-axis, the coordinate of the point on the graph is obviously a comma c. Now it's obvious whether x approaches a from the left or it approaches a from the right, the values of the function are not going to change. They will remain as a constant c. Obviously because this c is independent of x. But we can look at it intuitively in this way that as x approaches a from either side of a, the points on the graph approach the point whose y coordinate is c. So it's reasonable to take this c as the limit of c as x approaches a. So we have limit of c as x approaches a is equal to c. And we'll also discuss its formal proof, but not now. Now let's quickly look at one more limit law, which is the limit of x as x approaches a is equal to the number a. So this is another limit law, and its proof is also pretty straightforward. Let's look at it intuitively. Suppose this is our coordinate axis where I have 0 here. This is our x-axis, this is our y-axis, and let's say the line passing through the origin represents y is equal to x. And let's take the number a on the x-axis right here. Now we know that corresponding to this point a, the point on the graph has the coordinate a comma a. So this point is a on the y-axis. And this coordinate is obvious because all along this line, y is equal to x. So if x is equal to a, y has to be a. Now it is very easy to see that as x approaches a from either side of a, the values on the graph approach the point whose coordinate is a comma a, because the values of this function x approach the number a on the y-axis. So this point a is the limit of this function x as x approaches a. So this is how we get limit of x as x approaches a is equal to a. And now I'm going to share with you the list of limit laws which I have right here. So this is just the part of the list where you can see first 5 limit laws. Let's first see what is the statement of the limit laws. So it says, suppose we have gx and hx, any two functions, and c is a constant, and further we suppose that the limit of g and limit of h exist. In that case, we have limit of a sum is equal to the sum of the limits. And this is the first limit law that we just discussed in the beginning. Similarly, we have difference law, so which says that the limit of a difference is equal to the difference of the limits. And then we have the constant multiple law, which says that the limit of a constant times a function is equal to the constant times the limit of the function. And then we have the product law, which says that the limit of a product is equal to the product of the limits. And then we have the quotient law, which says that the limit of a quotient is equal to the quotient of the limits, with the condition that the limit of the denominator, which is this, should not be equal to 0. So in this way, we have more limit laws, which you can see right here. This law number 7 we just discussed, and the law number 8 we just discussed. Now see, the thing is that we'll be able to prove most of them once we have learnt the precise definition of the limit of a function as x approaches a, and which is quite a few lessons away, I would say. So for now, we'll take them as they are, and we'll discuss and apply them one by one as we'll come across the problems related to them. At a glance, this list might seem overwhelming to you because we haven't discussed or proved some of the laws yet, but as I said earlier, we'll come back and prove them once we have learnt the precise definition of the limit of a function as x approaches a. So starting from the next lesson, we are going to learn how to apply these limit laws while determining the limit of a function as x approaches a.